in the last lecture I showed you that if there is a basic feasible solution, then it must also be an extreme point, and I did try to explain to you that the two concepts, the concept of a basic feasible solution was through algebraic relationships, and the concept of an extreme point was in some sense a geometrical concept, but the two are one and the same. And I did also show you that if a solution, if an extreme point is degenerate, that means it has less than m components positive, then there will be more than one basic feasible solution which will correspond to the same extreme point. So, this was what we had done last time at the end of the lecture. Now, let me continue with that, and so the another important thing which helps you to, which gives you a good insight and also shows you what simplifications can be achieved by considering the structure of the problem. So, here I will talk about the representation theorem. And I will give the theorem first of all in its general form, in its general form. Okay. So, the idea here is that if essentially what we are saying is that if you have a convex set, a polyhedral set, and the polyhedral set is always defined by a set of linear equations and inequalities, then we want to say that it will have extreme points, and then any point in the set. Also, in the general form, when I talk about it, a polyhedron may also have directions, and so any point in the polyhedron can be expressed as a convex combination of its extreme points and non-negative combination of its extreme directions. This is what we want to say here. So, if P is non-empty, so I am always referring to a polyhedron by P. So, if P is non-empty polyhedron, then it has extreme points and extreme directions, right, and any point x belonging to P can be expressed as a convex combination of its extreme points and non-negative combination of its extreme directions. Okay, I will not prove the theorem because for a beginner it is not really necessary to go through the rigorous proof, but the idea is very important and we will keep using the result a number of times. So, essentially let me just go through the theorem again. So, if P is non-empty, we showed you that P is the same polyhedron. I am referring to the polyhedron P as x belonging to Rn subject to Ax equal to B, x greater than or equal to 0, right. So, set of equations and inequations define your polyhedron, which is same as your feasible set for the linear programming problem in the standard form that we have been discussing. Okay. We showed that if this is non-empty, then it must have a basic feasible solution. Right. I showed you that if there is any feasible solution, then you can always reduce it to a basic feasible solution. So, P non-empty implies there is a feasible solution, which means that there is a basic feasible solution, and from the result that I proved in the last lecture, that for every basic feasible solution is also an extreme point of the corresponding polyhedron. Therefore, there are extreme points here in P, and since number of basic feasible solutions is finite, therefore, the number of extreme points will also be finite. Remember, I gave you in a few lectures before this, I showed you there is an upper bound on the number of basic feasible solutions that a linear programming problem can have. Therefore, the number of extreme points is also finite. So, then what we are saying here is that so let x1 to xk denote the extreme points of okay, if you want to be more specific, denote all the extreme points on both P and D1 to DR, all the extreme directions then what we are saying is then x belonging to P can be written as x is equal to summation lambda I xi, I varying from 1 to k, plus summation mu I di, I varying from 1 to r, where summation lambda I varying from 1 to k is 1, lambda I is greater than 0 for all I, and sigma, no there is no sigma, and mu i's are also greater than 0 for all I. Okay. So, this is the general expression for, so therefore, what essentially is being said is that even though the feasible region or the polyhedron has infinity of points, feasible solutions, we do not need to be concerned, because every feasible solution can be expressed as a convex combination of its extreme points and non-negative combination of its directions. So, somehow if we can see the behavior of the objective function at these points, that will give us a clue, and that will follow, that theorem will follow after this one. So, this is the whole idea. Now, in case P is bounded, that is P has no directions, right. I showed you that if there are no directions, then your region will not extend to infinity, because having a direction means that you can go along, keep moving along that direction and stay feasible in the feasible region. So, P bounded implies that the P has no directions, right. In this case, in that case, x belonging to P can be expressed as a convex combination of its extreme points only. Okay, since there are no directions present, so therefore I can write this as a convex combination of its. So, let us take up an example. So, the general form had the directions present in it, and if there are no directions present, if your set is bounded, then I just need the extreme points to express any point as a convex combination of these extreme points, right. So, let me just show you, and I will take the finite the bounded case. So, suppose consider the polyhedron. Consider the polyhedron x1 minus x2 less than or equal to 3, 2x1 plus x2 less than or equal to 4, x1 greater than or equal to minus 3. So, this is all. no negativity conditions, no non-negativity conditions, and no equality equations to be satisfied, just this set of inequalities, right? Okay. So, let us draw the, so here if you take this as a 2 axis, x1 and x2, the first one when I write it as equation, this is x1 minus x2 equal to 3, at x2 0 it passes through the point 3 0. So, 1, 2 and 3, this is one point, and when x1 is 0 it passes through the point 0 minus 3. So, this is 1. This is one constraint, and less than or equal to 3. So, this side, because 0 is on this side, right. So, this is the part. Then this one gives you x2 0 gives you x1 equal to 2. So, this is 2, and x1 equal to 0 gives you x2 4. So, this is 1, 2, 3, 4. So, this is the other one, and again 0 is on this side. So, this is a portion, right. Then x1 greater than or equal to minus 3. So, I will have 1, 2, 3. So, if you draw this, if you can draw this as a straight line, then so this will meet it somewhere here. Okay, let's consider it as a point of intersection. So, this is your polyhedron. Okay. So, let me call, so this was your O, let me call this point as A, and this point as B, and this is C. So, 3 extreme points. This is a bounded polyhedron, right. Okay. And quickly, if you want to find out the points of intersection, x1 minus x2 equal to 3, 2x1 plus x2 equal to 4. This gives you 3x1 equal to 7. So, x1 is equal to 7 by 3, which implies that x2 is equal to 7 by 3 minus 3 from here. x2 is equal to x1 minus 3, 9. So, which is equal to minus 2 by 3. So, the point is 7 by 3. This is the point 7 by 3. So, this is 7 by 3 and minus 2 by 3. Okay. The point B is given by the intersection of these two. Then, if you want to look at this two, so x1 equal to minus 3 will give you what? You take it here. So, it will be minus x2 equal to 6, which means x2 is equal to minus 6. So, the point A is minus 3 minus 6. Right. Okay. And finally, if you substitute it here, that will give you x2 equal to 4 plus 6, which is 10. So, this point, the point C is minus 3 and 10. Okay. So, that gives you the extreme point. Now, of course, I must point out that for a small example, I am able to find out all the extreme points, but essentially the representation theorem does not require you to find all the extreme points. What I am going to demonstrate is that you can have this representation, and therefore, you can simplify a lot of things, but if you had to find all the extreme points, then there will be no fun, because it will require much more effort than maybe actually solving the problem. So, therefore, here I am just trying to show you what we mean by this representation theorem. So, I am saying that if you, for example, take a point here, then you know that it is on the join of these 2 points. So, it will be some convex combination of A and C, and I can find out the corresponding. So, if I am given this point, I can write it as I can find my lambda such that lambda times this plus 1 minus lambda times this is this point, right. If you have any point here, for example, yeah, then what do you do? See, the thing would be, there can be many ways, need not be what I am showing you is the only way. So, you can have this example, you can join this to one of the extreme points, extend the line to meet it here, yeah. And then you see that, so this point can be written as a convex combination of these two, yes. Then this itself can be written as a convex combination of B and C. So, the final thing when you write this point, this will be a convex combination of A, B and C. So, let me demonstrate this to you, and I will take up this example. Say consider the point 0, 1. So, I am taking the point 0, 1. So, let me say that it is here, okay, and this point is 0, 1. And how do I, so there can be many ways of doing it. So, here 0, 1, let me write it as lambda 1 times minus 3 minus 6 plus lambda 2 times 7 by 3 minus 2 by 3, yes, plus lambda 3 times minus 3 and 10. Right. I write this and I say that lambda 1 plus lambda 2 plus lambda 3 is equal to 1, lambda 1, lambda 2, lambda 3 all greater than or equal to 0. So, all I have to do is to demonstrate to you that lambda 1, lambda 2, lambda 3 exist, and then you have the point 0, 1 as a convex combination of this, right. So, here what are the three equations that you get? The first one is minus 3 lambda 1 plus 7 by 3 lambda 2 and minus 3 lambda 3 is equal to 0, right, component wise. And the second component gives you minus 6 lambda 1 minus 2 by 3 lambda 2 plus 10 lambda 3 is equal to 1, and you have this. So, 3 equations, 3 unknowns, and you should be able to find them, find the 3 unknowns lambda 1, lambda 2, lambda 3, yes. So, maybe we can spend just a little bit more time. So, if you multiply this by 2 and then subtract, so this lambda 1 will cancel out, and so you will have 14 by 3 and I am subtracting. So, my 14 by 3 minus 2 by 3 minus 16 by 3 lambda 2, then this will be minus 6, so plus 16 lambda 3 is equal to 2, is equal to 1, sorry. I have taken twice this and then subtracted. So, this is because there the right hand number is 0, right. So, then I can find out. So, here okay. So, one can go on and doing it, say here lambda 2, lambda 3 I have, and also from this one I can use from this one here. Yeah, the numbers are not very good, so therefore, I was wondering if okay. So, the other one would be if I substitute for lambda 1, okay, let me do it here. Let me do it in this one. I substitute for lambda. So, lambda 1 is equal to 1 minus lambda 2 minus lambda 3 from this one, right. So, let me substitute here in this equation. So, that will be minus 3 times 1 minus lambda 2 minus lambda 3 plus 7 by 3 lambda 2 minus 3 lambda 3 is 0, right. So, now simplify, that will give you plus, see this is plus 3 lambda 2 and this is 7 by 3. So, 16 by 3 lambda 2, then this is plus 3 lambda 3 and so this simplifies. So, plus lambda 3 minus 3 lambda 3 is 0. So, you are left with this is equal to 3, good. So, therefore, I immediately get this implies lambda 2 is 9 by 16. So, once I have lambda 2, then from here I can get lambda 3, and once I have lambda 1, lambda 2 and lambda 3, then I get lambda 1. So, this is what you have. The other method that I was demonstrating to you would be, see for example, do this. I will just revisit the polyhedron. I gave you the equations, the inequalities that define this polyhedron earlier, right, and I was trying to show you. So, these are the 3 extreme points, your feasible region or the set of the points that constitute your polyhedron is the shaded portion, right. And I was trying to show you that how you can express any point in the polyhedron as a convex combination of these 3 points, because they are because the polyhedron is bounded, there are no directions present. So, only 3 extreme points. So, I said that if you took a point on this line joining A and C, then you see this can be expressed as a convex combination of A and C, right. If I take any point inside the polyhedron, then I can join it to one of the extreme points and then extend the line to meet one of the equations defining the polyhedron, and this point will be a convex combination of these two, and since this itself can be written as a convex combination of A and C. So, finally, this point will be a convex combination of A, B and C. Now, while I was trying to show you how we will represent the point 0, 1, I took it to be in here, right. So, actually the point is this one. So, the point is 0, 1, right. And so, whatever calculations I did after that is all okay. I just, because I took the point 0, 1 here, therefore, I said that your lambda 2, because see we tried to express 0, 1 as lambda 1 times minus 3 minus 6 plus lambda 2 times 7 by 3 minus 2 by 3 plus lambda 3 times minus 3 and 10. Okay. And so, since I had taken the point here, I made the remark that lambda 2 must be 0, but actually 0, 1 is a point which is inside the polyhedron, and therefore, lambda 2 came out to be non-zero. So, the calculations were okay. It is just that, so whatever I said afterwards all follows, except that I took the position of the point 0, 1 as not correctly, and therefore, with the correct position of 0, 1, the calculations are okay. As some lambda times the point minus 3 minus 6 plus 1 minus lambda times the point D, which you can say the coordinates are maybe let us say x1, y1, the point D, right. Then x1, y1 I can write as lambda minus 3 minus 6 plus 1 minus lambda times, now the x1, y1 itself I can write as a convex combination of B and C, right. So, I will say that this is mu times this is 7 by 3 minus 2 by 3, right, plus 1 minus mu times minus 3 and 10. Okay. So, now does it give me a convex combination of the 3 points? Yes, because you can show that the coefficients are all. So, here lambda and mu are non-negative, otherwise I am taking lambda 1 minus lambda. So, essentially you are writing the point as lambda times minus 3 and minus 6 plus mu times 1 minus lambda, then 7 by 3 and minus 2 by 3 plus, okay, and this is 1 minus lambda, 1 minus mu. So, 1 minus lambda, 1 minus mu minus 3, 10. Yes. So, now it is is it a convex combination of the 3 points? Yes, because all the components are non-negative, the coefficients are non-negative, and you see that this is a convex combination of the 3 extreme points, since lambda plus mu 1 minus lambda plus 1 minus lambda 1 minus mu. If you open up the expressions, right, this will be lambda plus mu minus mu lambda here, then you have plus 1 minus lambda minus mu plus lambda, right. And you see the lambda cancels with lambda, mu cancels with minus mu lambda this, so this is equal to 1. So, this is a convex combination, essentially this is what I wanted to show you. So, now the next result that I will give you will show you the actual simplification in the presentation of the linear programming problem, and hence the algorithm, very efficient algorithm, can be efficient in the practical sense. I am not talking in terms of practical, in terms of technical sense, because there is a proper definition when you say algorithm is efficient. So, I do not mean that way, but certainly there is a lot of simplification. So, the calculation here needs to be checked, and I will give you the corrected calculation next time. Okay. So, the result that we are going to talk about now is that, so this is a theorem for LPP3, a basic feasible solution is an optimal solution. Is an optimal solution. Okay. This is the whole idea behind it, that now I can say that I do not have to worry with the whole feasible set, which has infinity of feasible solutions. If I can prove this result, then it means that I just have to check out a finite number of basic feasible solutions and pick up the one which is the best, right. So, but here LPP is a basic feasible solution is an optimal solution. I am assuming here, the assumption is that the LPP3 has an optimal solution, right. So, I will state that first, prove. So, we have assumed here that the LPP3 has a finite optimal solution, right, which I mean to say is that the optimal solution exists. It is possible that the optimal solution may not exist. So, I am working with the assumption right now, and then we will come back and show you that that assumption is not really needed. So, we have assumed here that the LPP3 has a finite optimal solution. This implies that LPP3 has a feasible solution. Okay. If there is an optimal solution, obviously there has to be first a feasible solution. If there is a feasible solution, with this implies that LPP3 has a basic feasible solution. Remember, I showed you quite some time ago that you can always reduce a feasible solution to a, and now with our result that I proved in the last lecture, the corresponding P has extreme point. So, P has an extreme point, and so let us assume that it has a finite number of extreme points, and we will use our representation theorem now. So, existence of a finite optimal solution implies that a basic feasible solution exists, and therefore extreme point exists, and since there are no since it has a finite optimal solution, I can also assume that there are no directions in P. Why? Because the optimal solution is finite, so it is clear to me that even if the region is not bounded, I can bound it because my optimal solution is finite. So, I am not disturbed if the region is unbounded, and I will talk about it later on again. So, P has an extreme point. So, therefore, now suppose and maybe I will add here P has an extreme point and no directions. And has no directions, right. Okay. So, suppose x1 to xk are the k extreme points of P. So, here P is the polyhedron corresponding to the feasible set for LPP3, right, points of 3. Then, so these are the extreme points, therefore, by the representation theorem, suppose this, and let X be any feasible solution, and let X be any feasible solution by the representation theorem. X can be written as summation lambda I x I varying from 1 to k, summation lambda I equal to 1, I varying from 1 to k, lambda I greater than or equal to 0 for all I. Okay, by the representation theorem which we just talked about, you have this, right. So therefore C transpose X is equal to summation lambda I C transpose Xi, I varying from 1 to k. Now remember, lambda i's add up to 1, and so here this you can say is therefore greater than or equal to sigma lambda I varying from 1 to k times minimum of C transpose Xi, 1 less than or equal to I less than or equal to k. See, if I replace each C transpose Xi by the minimum, so therefore I have these k numbers, so I have these k values C transpose Xi, I varying from 1 to k, I have these k numbers, I choose the smallest one, whichever, so I call it the minimum of all the C transpose Xi. Then if I replace each C transpose Xi by the smallest one, then since lambda i's are non-negative, I will have this inequality and all these lambda i's will get added up together. This is equal to 1 by my condition. So therefore this reduces to minimum of C transpose Xi 1 less than or equal to I less than or equal to k, right. And suppose the minima occurs for which is C transpose X some s or some s, right. So therefore for any feasible solution, what have I shown you? That the value of the objective function will be greater than or equal to the value of the objective function at a point at one of the extreme points, which corresponds to the extreme point for which this value is smallest. So out of these k extreme points, I have computed the value of the objective function at these k points, chosen the minimum one, and suppose that corresponds to C transpose Xs, then every feasible solution will have its objective function value higher than the value C transpose Xs. Of course, there can be more than one extreme point for which this minima occurs, right. Okay. So that shows that this must always, that means there will always be an extreme point which will correspond to the smallest value of the objective function, of course with the assumption that there is a finite optimal solution to the standard linear programming problem, right. And so therefore this implies that the optimal solution will always occur at an extreme point. So I am not denying here that there may be many other points at which the optimal solution will occur, but what I wanted to show you is that an extreme, that it will always occur at an extreme point, right, which implies that a basic feasible solution will always be an optimal solution. Now let me, am I wording it for a basic feasible solution will always be an optimal solution. Okay. So so essentially what it boils down to is that our search for an optimal solution can only be now contained to finding a basic feasible solution, because after I have shown you that there is a basic feasible, an extreme point is also a basic feasible solution, then if optimal solution occurs at an extreme point, that means it occurs at a basic feasible solution, which means that I only have to search among the finite basic feasible solutions and find the optimal one. But again, this does not tell you that you can do away with a regular algorithm, because this number of basic feasible solutions is an exponential one. It can be very high. Remember, the upper bound that I gave you was NCM. So with n large and m also reasonably large, then this number can be very big. And so the question of finding out all the extreme points or all the basic feasible solutions and then computing the value of the objective function will not be a very efficient way of solving this linear programming problem. So we have to judiciously search among the feasible basic feasible solutions and find the best one. Now see, in the last result I showed you that there will always be a basic feasible solution which is an optimal solution for a linear programming problem, provided the linear programming problem has a finite optimal solution. I would like to show you maybe as a matter of theoretical interest, or the result will be used at some other time. But now I want to show you that if x is a basic feasible solution of, again let me keep referring to a linear programming problem in the standard form. So if x is a basic feasible solution of LPP3, then there exists a cost vector C such that x is the unique optimal solution of LPP3. Okay. So I hope the significance is clear here. Earlier I showed you, given a linear programming problem, there will always be a basic feasible solution which is an optimal solution. Now here I am saying that if you give me a basic feasible solution of a linear programming problem, I can find a cost vector. Okay. If I say LPP3, so here I am saying that C is not given. So now I will specify the C. So given a basic feasible solution, I will give you a C, so that this basic feasible solution is a unique optimal solution of the corresponding linear programming problem. Okay. So let me define. So I just have to give you, so let B be the basis corresponding to the basic feasible solution x, and define Cj as 0 if Aj belongs to B and 1 if Aj does not belong to B. So this is a clear definition of my vector Cj. Of the vector C, the component, the jth component is 0 if Aj is in B, and if Aj is not in B, then the value of Cj is 1. So if I define Cj like this for all j 1 to n, right, then you see what is the value of, so then C transpose x is 0, yes, because B is the basis corresponding to the basic feasible solution x. So for all the Cj's corresponding to Aj and B are 0, that means here when x is positive and x is a basic variable, the corresponding C is 0, Cj is 0, and when x is non-basic, then xj is 0, and so the corresponding Cj is 1. So this value, then C transpose x is 0, right? And for any feasible y, for any feasible y, C transpose y is greater than or equal to 0, which is C transpose x. Yes, because any other feasible solution will have, yes, at least one component different from x and so the corresponding Cj is 1. So, for any feasible solution, the value of C transpose y will be, or it could be 0. So, we are saying that C transpose y is non-negative, but C transpose x is 0. So, that means for any feasible solution, C transpose y will always be greater than or equal to C transpose x. Therefore, x is an optimal solution. Right. Now, we want to show that it is a unique optimal solution. So, to show uniqueness, of x, suppose, so that means there is no other, I want to show you that if there is any other solution, feasible solution, which has the value of the objective function as 0, then it must coincide with x. So, to show uniqueness of x, suppose y is a feasible solution such that C transpose y is 0, because the optimal value is 0. So, therefore, if there is any other feasible solution which is also optimal, then the objective function value must be 0, right. So, C transpose y is 0, which implies that yj such that aj does not belong to B, yj is 0, right, because you see the value of the objective function is the cost coefficients are such that this is 1 if aj does not belong to B. So, if any feasible solution has the objective function value as 0, then the yj value corresponding to the aj such that aj is not in B has to be 0. Otherwise, I will add a corresponding 1 here. So, the value of the objective function will not be 0. Remember, your y's are all non-negative. So, and if your c's are also non-negative, the objective function value will always be non-negative. To say that it is 0, I must have that yj such that aj does not belong to 0, which implies that y is a solution of B y b equal to 0, because for all j such that aj is not in B, the corresponding yj is 0. So, the system ay reduces to this, where yb are the components corresponding to the aj's which are in B. So, byb is 0, this is equal to B, right, which implies that yb must be B inverse B, and this is equal to your xb. Here again I am referring to xb as the part of the basic variables, because x is a basic feasible solution. So, therefore, this and xj is equal to yj is 0 for all non-basic xj. See, right, the value of the objective function is 0, and we already said in the beginning that the yj must be 0 such that the corresponding column is not in B. So, the non-basic variables anyway agree, the non-basic values agree, and now the basic values also agree, which implies that x is equal to y. So, that shows the uniqueness of the solution. So, therefore, I can always construct the cost vector such that any basic feasible solution will be the unique optimal solution corresponding to that. Now, in the previous theorem, let me just revisit. In the previous theorem, we showed that the LPP 3 will always have basic feasible solution as an optimal solution, right. Now, I should have added to it another part, and that is, now if it has q basic feasible solutions, which are optimal, then their convex combinations THEIR, then their convex combinations are also optimal. So, in that case are also optimal. See, I was reminded by the word, because here we have shown uniqueness. So, what we are saying now here is that if in case the basic feasible solution is not a unique optimal solution, then there will be more than one. So, if you have q basic feasible solutions which are optimal, then their convex combinations will also be optimal. That means there will be infinity of optimal solutions. So, either you have a unique optimal solution or you have infinity of them. Okay. And this part is not difficult to prove. Let me do it right here. So, suppose, so let x1 to xp be optimal basic feasible solutions, right. Then C transpose summation lambda I xi, I varying from 1 to p, is equal to sigma lambda I C transpose xi, I varying from 1 to p, where your sigma lambda I varying from 1 to p is 1 and lambda I greater than 0 for all I. Okay. But since all are optimal, they are all equal, right. So, this implies this is equal to summation lambda I varying from 1 to p times C transpose xs, whatever it is, because all are equal. So, where C transpose xi is C transpose xs for all I, 1 to p. Yes. Now, this is equal to 1. So, this is C transpose xs. So, we know that because it is a feasible region is convex. So, this is a feasible solution, and we are showing that the value of the objective function at this convex combination of the optimal basic feasible solutions is also giving you the same objective function value, and therefore, this is also optimal. So, that means if you have essentially what we are saying, if you have 2 points, 2 basic feasible solutions, and so corresponding to extreme points, if they are optimal, then any point, every point on the line joining the 2 optimal basic feasible solutions is also optimal. Okay. From the above theorem, we conclude that the set of optimal solutions of an LPP is a convex subset of P, the polytope which corresponds to the feasible region F for the LPP that we have been considering so far, which is in its standard form, right, and it is a face of P. Now, this I would like you to prove by finding a supporting hyperplane, just like the exercise that I did obtaining faces for or supporting hyperplanes for different faces of a polytope. I want you to here find out the supporting hyperplane and show that the collection of all optimal solutions of a linear programming problem is a face of the polytope P, which corresponds to the feasible region, and thus therefore, we can then conclude that every convex combination of a finite number of optimal solutions is an optimal solution. So, let me just consider show you the I have collected a few assignment problems which it would be worthwhile for you to go through, and I will give you some comments here for each problem, so that it will help you to work them out yourself. Okay. So, the first problem is consider the polyhedron P described by certain inequalities of both kinds, less or greater, right. Then I am saying that consider each of the faces Fi, which is given by making one of the inequality constraint as an equality constraint. So you have 5 faces because there are 5 constraints. So you have 5 faces, and then I am saying which of these Fi define a facet. That means you have to now tell me that if you take one of the inequations as an equality, then are there other inequalities also satisfied as equality or not. So, because remember the dimension of a facet is 1 less than the dimension of the polyhedron. So, here the polyhedron is of dimension 3. So, you have to show me that which are the facets which are of dimension 1 less than the dimension of P, right. And then I am saying that for F1 and F2, that means F1 corresponds to the first inequality being taken as equality, right, and F2 corresponds to the second inequality being taken as equality. So, find the vectors C1 and C2 such that max, so now here it is a maximization, right, change from minimization, so that the maximum has F1 and F2 respectively as a set of optimal solutions. So, you have to find, so now I have given you this construction here. So, please try, it will be very interesting if you can really construct your C1 and C2 such that all points in F1 are maxima points for the objective function with cost vector C1, and all points on F2 are maxima points for the cost vector C2. So, now let us go to problem 2. Formulate the problem of finding the shortest path between two nodes in a graph with edge weights Dij. So, that means if you join the node I and j, traversing that edge, the weight or the cost of that edge is Dij, or the distance. Representing distances as a linear programming problem, you may define variables xij for each edge ij each edge ij. So, we are saying that okay, the capital E represents the collection of all the edges, and I and j or I refers to a node. So, you have a graph here in which you have these nodes and you have joined some of the nodes, not all are joined. So, I comma j within brackets denotes an edge. So, E is the collection of all the edges, right. So, we say that xij is 0 if edge ij does not figure in the shortest path, and xij is 1 if edge ij figures in the shortest path. So, this will be because we have to compute the shortest path. That means, you take a node, or okay, now you might say that I have not given you the nodes from which for which the path has to be found. So, just fix a node, let us say fix node 1 and node n as the two nodes between which you have to find a path, and such that when you add up the weights or the distances of the edges, they must be the smallest. That means, there will be many paths from 1 to n. You have to find a path for which this weight is shortest. Okay. This is the problem, and what you have to take care is that you see at every node, if a path is entering a node, then it must also leave that node. So, you have these conservation constraints. So, your objective function will be summation Dij xij over all ij in E, because xij will be 1, then you will add the weight. If xij is 0, you will not add the weight. So, your objective function is fine. Now, your constraint and the variables are xij equal to 0 or 1. So, here again I chose this problem because I wanted to show you that it is not enough to always describe a problem by saying that your decision variables are non-negative. You might also have here discreteness. That means, you only allow xij to take a value 0 or 1, right. And then the node conservation constraints are necessary here to formulate the problem correctly, and you have to say that summation xij over j, that means from I you are going to j node. So, there may be many such nodes. So, all this summation must be equal to the edges which are leaving the node. So, that means minus this thing here. So, node conservation constraint I am saying node conservation. So, this is summation xij j. So, here I will not say anything because whatever edges are nodes are being joined by this minus summation xji, again summation over j here, or okay, this is sigma xij minus, yeah, these are going out and these are coming in. So, this should be 0. This should be 0 when I is not equal to 1 or n. That means, I am saying you have to determine the path from 1 to n. So, what will be the node conservation for? So, here it will be x1 j. summation over j. This you want as 1, because we have a node I here, then you have an arrow like this and you have an arrow like this. So, it depends, sometimes some people say, put this as a -1 or this as a -1, does not matter, that will not be important, because once you stick to one convention then it is okay. So, when you take the node 1, then you are saying that all, because I am wanting to find a path from 1, right, and here you have n here. So, from node 1 you only want the arrow to go out, you want the path edge to go out, nothing should come in, because you want to determine the path from 1 to n. So, therefore, here I will say sigma x1j is 1, right, only one edge will be chosen for the shortest path. And similarly, here when you write this, this will be summation xjn, summation over j, this will be -1, because when you are saying that the sign for the edge entering, so here also for the sign for the edge entering, so xji is minus, right. So, here minus xjn, this is minus. So, except for these two, otherwise for node conservation you are going to have zeros. So, now I come to problem 3. I have just asked you to find all feasible solutions of the following system, all the basic feasible solutions. So, remember you have to, because the two constraints, so pair 2 columns at a time and find out which of them give you a basic feasible solution. Okay. Then for problem 4, okay, fine. So, again I have given you a system of linear equations and I have given you a feasible solution 1 2 1 1 0 0. I am saying, is it a basic feasible solution? And you remember that because four variables are positive here, that means if the corresponding columns are linearly independent, it will be a basic feasible solution. If the corresponding columns are linearly dependent, it will not be a basic feasible solution. So, I have asked you to construct a basic feasible solution from it. Problem 5, I have given you a solution which is known to be an optimal. So, there is a linear programming problem. I have given you a solution which is known to be an optimal feasible solution, but it is not a basic feasible solution. So, here again, because I have discussed enough constructions how you move from a basic feasible solution to another, also improving the value of the objective function. Now, here there is a twist. Here I do not want you to improve the value of the objective function, I want you to maintain the value of the objective function the same, because the given solution is optimal. So, whatever the value of the objective function here, so you have to go through the proof in which I showed you how to move from one basic feasible solution to another while improving the value. So, just go through that proof and you will be able to find out how you should move on. I have given you a note here also. Now, in the 6th problem, show that the converse of the theorem that if two distinct bases correspond to the same basic feasible solution x, then x is degenerate, is not true. The converse, that is, there can exist a degenerate vertex whose corresponding basis is unique. So, you can construct a system of linear equations and then try to show me that how a degenerate vertex may correspond to only one basis. In the 7th problem, I have given you 5 vectors and I am asking you to construct the convex hull. Illustrate geometrically the collection of all convex combinations of these 5 points. Identify the vertices of the convex set obtained. Then 8 and 9, again I have given you 2 polyhedrons and I am asking you to identify the faces, extreme points, extreme directions of the set. So, I hope you enjoy going through this assignment sheet.